A hospital autoclave made of steel has a mass of 32 kilograms. It is filled with 352 grams of water. The temperature of both is 23.7 degrees Celsius. You want to heat them both to 100 degrees Celsius. To do that, you will use the heat given off when you burn cyclohexane. If all the heat given off when burning the cyclohexane is used to heat the autoclave filled with water, how many grams of cyclohexane will you need to burn to achieve that? So I did a quick sketch. We got autoclave, which looks like a closed system because all the cyclohexane that is being burned, the heat is going into the steel and the water. So we also got the specific heat capacity of water and the steel, and also the enthalpy of the cyclohexane. The burning of the cyclohexane, combustion. Here we'll need to set up the energy exchange equation for the closed system. So basically, the heat will be given off by the cyclohexane and taken up by the water and steel. So in this case, the energy that's required to heat the water and steel will be equal to the energy that is given away by the combustion of cyclohexane. So to get the energy to be consumed by water there's the formula: mass of water times specific heat capacity of water times the difference in temperature. We'll do the same exact equation for the heat taken up by steel, which is we use mass of steel, specific heat of steel, and delta T for steel. Now for the energy given off by the combustion process is a little bit different because we don't have the specific heat capacity. We were given the enthalpy, specific enthalpy for the cyclohexane, but also the enthalpy is shown in kilojoules per mole, not kilojoules per gram, like it's shown for the specific heat. So we'll have to convert that from kilojoules divided by mole into kilojoules per gram. So therefore, in order to do that, we have to take the specific enthalpy given to burn the cyclohexane and divide that by the molecular weight of the cyclohexane. Okay, so here we go. The energy taken up by the water, we just plug in the mass, the specific heat capacity, and the delta T. So here we got 112.265 kilojoules. Now we do the same thing for the steel. We've got the mass of steel at 32,000 grams. Don't forget to convert the 32 kilograms into grams because the specific heat is given in joules per gram, not joules per kilogram. And we want to write an equation in the same units. So here we have 32,000 grams multiplied by the specific heat capacity of steel and multiplied again by the difference in temperature. So here we got 1,100.16 kilojoules. So for this formula here, we're going to rearrange this equation right here because we will know the heat required to be put out by the burning of cyclohexane, because this is our equation: QW plus QS equals to QC. So we just found the energy required by the water. We just found the energy required by the steel. So since we know these two, we will know the energy that is needed to be put out by the cyclohexane. So in this case, the unknown is mass of the cyclohexane. Okay, so to rearrange this equation, we get mass of cyclohexane equals to the energy put out by the cyclohexane divided by the specific enthalpy of the cyclohexane expressed in kilojoules per mole, and to change that into grams we have to multiply it by the molecular weight of cyclohexane. So once we do all that, the mass that's required to be put out for cyclohexane, or the mass of cyclohexane, is 25.4 grams.